Hi, everyone, and welcome to another FLAN Talk. Today we have Nouha Dziri presenting. She's a postdoc researcher at the Allen Institute for AI and is working on the Mosaic team. Prior to this, she completed her PhD at the University of Alberta, where she worked with Alberta Machine Intelligence Institute. And she worked at Google Research, Microsoft Research, and Mila. And her research interests lie in the understanding the capabilities of large language models and making them trustworthy. And today we'll hear from her about her paper, Faith and Fate, the limits of transformers on compositionality. Thank you for being here today, and you can take it from here.
Yeah, thank you, Lena, for the intro, and thank you for the invite, Marco. I'm so excited to be here today and to tell you about our new work called Faith and Fate, Limits of Transformers on Compositionality. This is a work, actually, it's the outcome of a fun collaboration with awesome people at Mosaic, at AI2, and also awesome people at the University of Washington. Okay, so as you may know lately, there is this common perception in the media and research community that ChatGPT, GPT-4, etc., are almost at the point of achieving AGI, and people started worrying that language models are going to take over humanity, etc., etc. So we believe that these claims are a bit exaggerated, and in this work we try to demystify transformers and shed light on their true capabilities. Oops. So here one of the questions that we asked, does sparks of AGI, meaning GPT-4, solve a trivial task like that we humans excel at, like multiplication? So what we did, we actually tried to ask GPT-4 to give us an answer for this simple 3-digit by 3-digit multiplication. And then GPT-4 gave us this, answer that looks pretty plausible. But when we looked closely at it, it's actually wrong. So we decided, let's ask again GPT-4 to give us a step-by-step answer for that. And then GPT-4 gave us an answer, but still, again, this response is still wrong. So we decided to do a large-scale evaluation, and we found that GPT-4 is only good 3-digit by 3-digit multiplication at about 60% almost accuracy. So this might appear that good enough, right, for some of you that, okay, GPT-4 is mastering 3-digit by 3-digit by 60%. It's actually worse. If we just add 1 digit and ask 4 by 4-digit multiplication, it goes to 4%. And if we ask 5 by 5, it goes to 0%. So what's happening here? So before I delve deeper into this, let me stop here a little bit and share with you how our work was received in the community. So the great Kevin Murphy, the author of this amazing machine learning book, tweeted that he absolutely loved our paper and how we did these analysis. Another tweet described the work as the best paper they've ever read, and no excessive hype, clear question, rigorous empirical evaluation. Now, the reason I'm telling you about this is not to brag about it, but I really want to emphasize on why we embarked on this work. So currently there is this overwhelming amount of hype surrounding transformers, and we really felt the need to cut through the noise and to truly explore the limits of these powerful models. So why do they fail at multiplication? Maybe the model hasn't seen enough multiplication data during training. So we thought about how about exhaustively training GPT-3 on a huge amount of data. Maybe in that case, if it has seen enough training data, it would be able to answer 3-digit by 3-digit or even bigger digit equations. So this is what we did. Since we can do it with GPT-4 and we can only fine-tune GPT-3, we actually used 1.8 million examples up to 4 by 2 multiplication meaning 1 by 1, 2 by 2, up to 4 by 2. And then we answered GPT-3 after there's a huge amount of training to answer the same, like the 3 by 3 digit, and it still fails. So we found out that it's only accurate as about 55% of the time, although it has been trained on a huge amount of data. So it doesn't seem that exhaustively will, make the model learn how multiplication works. So we were thinking, maybe this is a tokenization issue. Maybe the model is able to learn, but the way how we tokenize things is wrong. We decided let's train GPT-2 from scratch on multiplication data. So basically here, we try to assign each digit to one token, and each math symbol as well, like equal or multiplication, is assigned to one token. And we train GPT-2 XL on up to 4 by 4 digit multiplication, which amounts to 19 million data points in total. Unfortunately, we discovered that GPT-2 XL, without being even training on language data, it's very poor performance, about 10% accurate on 3 digit by 3 digit multiplication. So actually, like transformers without any language pre-training are almost useless in this case. And here, yes, it doesn't seem that tokenization is the issue for this low performance. So we decided. So far we did zero shot and fine tuning on a huge amount of data. Let's try to show the model the step-by-step solution, or what we call the Scratchpad. So basically, we prompted the model with a few examples with the hope that they can acquire how multiplication works or the rule of multiplication. And then we asked GPT-4 to just follow the steps and provide an answer. And, the performance increased tremendously from like 50% to 92%, which is amazing, right? So here you may think, transformers, by just, showing them few examples on how to solve multiplication, we can crack and how they can crack multiplication and they can solve it, which is amazing and great. But we said, okay, how about we just test a little bit more compositional cases? And we asked to solve 4 by 4 using the Scratchpad. And the performance of these language model goes actually to 4%. And the more compositional, it even degrades further and further. For 5 by 5 multiplication, it goes to 2%. So here, before going any further, I actually want to stop a little bit and discuss some of the questions that arise in the community. So previous work have said that transformers absolutely can learn through multi-step algorithm in context, and it can generalize to arbitrary problem sizes, et cetera. And there is this paper from Google that says teaching algorithmic reasoning via in-context learning, and they show that by using some algorithmic prompt, they can improve the multiplication performance compared to the baseline tremendously. And this is true. I mean, we're not denying that, but in this paper, they have a different graph from ours, and they're trying to improve the model performance to achieve, so basically their goal is to achieve partial mastery. But even in that paper, they actually acknowledge that GPT-3 doesn't do well on multiplication, on multiplying digits that are larger than 3. And then basically what they do, they try to convert the problem manually to addition over small digits that are less than 3 multiplication. So here what I want to say is that our goal is different. We try to investigate the fundamental limits of achieving full mastery of the task rather than just incremental improvements. Just I'm gonna close the parentheses here and move to continue about the work. And basically, so we tried so far zero shot, few shot, and fine tuning without a Scratchpad, and do few shot with a Scratchpad. How about we fine tune GPT-3 on Scratchpad, meaning showing the model all the steps required to solve multiplication? This time, this should basically solve the task. But we discovered that the data size for multiplication increases exponentially with the addition of just one digit. And you can see that this is reflected in the training cost. For example, fine-tuning GPT-3 on up to 5 by 5 digit multiplication, it can cost us approximately 700 million, if not more. So we don't have that budget. We decided to just, train it on up to 3 by 2 and see what happens, explore its performance. So yeah, if it's failing, it should be the same for 5 by 5. So we fine-tune GPT-3 and it actually achieves amazing performance on in-distribution data, 96%. But the problem is that it drops sharply to 0 on OOD cases. Like the minute you show it like, equation that's not within the training data, like for example, we train up to 3 by 2 and you show it 3 by 3 or like 4 by 2, it actually fails. So what's the problem here? Yeah, so this is something we try to explore after archiving the paper. It's not there yet, but I wanted to share with you. We tried to work on some Grokking experiments, and by Grokking here I mean training long enough after overfitting. And some existing work said that by training long enough, generalization can happen. So we decided to train GPT-3 on the multiplication data with Scratchpad and without Scratchpad, and we wanted to see what happens, whether this would actually solve the problem. Actually, we trained very long, far exceeding the point at which the accuracy happens, like the in-domain accuracy plateaus, which is 90K steps for the case without Scratchpad and around I think 15K steps with Scratchpad. And it cost us a huge amount of money, in total 90K USD in order to train these things. But now this is good, right? Let's see how it performs, whether it's actually solving multiplication. And we noticed that even with this really prolonged period of time, GPT-3 still exhibits poor performance on OOD, although it's still performing pretty well on in-domain cases. So basically here we hypothesize that the extent to which generalization improves beyond overfitting is really linked to the inherent complexity of the task. And it seems that for the task of multiplication, the complexity makes it even more challenging to learn very well structured representation. And this might lead to failure to achieve Grokking. Now, compared to previous works, they have explored, yes, they show that, training long enough can help the model generalize to unseen cases, but, the tasks that they considered were not compositional enough, and they were quite easy to solve. But so I don't want to say anything concrete here, but of course, additional experiments and future work is needed to really understand how Grokking works, why it works, would it work for such a complex case? And it would be really interesting for those who have enough compute or enough budget to investigate this further. We couldn't do it ourselves. We already spent a huge amount of money. Plus, something I wanted to mention is that, it seems that it's not very efficient to, continuing spending a lot of money on something that might not be scalable for like very complex tasks. So it would be more interesting to invest in smarter algorithm in order to solve the generalization problem rather than just trying to push training further and further, especially for those who don't have enough compute and budget. So this is about Grokking. To go back to our paper and how we try to understand the behavior of transformers, we try to understand this behavior, why it fails and why it succeeds. And we decided to see whether we can, understand their performance using computational graphs. So before going any further, why multiplication? Actually, we don't only look at multiplication. We look at other tasks such as dynamic programming and also a more natural language task, which is the Einstein puzzle that I will discuss in a bit. Now we looked at, I'm talking at multiplication because it's a trivial for a lot of people and it's easier to understand. Of course, we looked at these tasks not for the sake of solving multiplication, but because they require compositional multi-step reasoning, and these are very crucial and very, very wonderful tasks in order to understand the behavior of these language models when dealing with compositionality. So we frame the problem of all of these tasks as a computational graph. So basically here, the nodes represent the partial solution, and the branches represent operators that can be applied in order to modify these solutions. So here you can think of the, the computational graph as a tool to understand what's going on. Basically here, one of the observations, we found that the model performance decreases as the graph complexity increases. And in order to measure the graph complexity, we used three metrics: the graph width, the graph depth, and also the average parallelism, which is the ratio between the number of nodes and the depth of the graph. So you can see here the number increase when we increase the complexity of the graph. And then a common, conclusion among all of these tasks, all the models that we experimented with, is that GPT models cannot fully solve compositional tasks, and as we increase the complexity, the accuracy goes to zero. So the second task, as I mentioned, we consider dynamic programming, and we considered a classical dynamic programming task, which is the non-adjacent maximum sum subsequence. Dynamic programming, obviously, it recursively breaks a complex problem into simpler subproblems. And basically, for this classical problem, the task is to, giving this list of integers, we need to find the subsequence with the highest sum, such that no two numbers in the subsequence are adjacent in the original sequence. So in this case, we have, 4 and 4, like the solution is 4 and 4 and 1, which is equal to 9. So this problem can be solved in O(n) time, and we restrict the, each integer to be between the interval of -5 and 5 range. So similar to multiplication, we noticed that out of the box, performance goes to zero with increased complexity. Obviously, GPT-4 is performing better than GPT-3 and GPT-3.5, but it's still, the minute we increase complexity, it goes to zero. Now, we also, similar to multiplication, we used Scratchpad, we used a few short examples, we used fine-tuning, we used all of these things to see whether this can solve the problem. And we noticed, yes, using Scratchpad improves the performance, and fine-tuning improves, but still, in domain cases seems to work pretty well, but the minute we test on OOD cases, the performance goes to zero. Now, moving on to the next, task that we consider, we call it the Einstein puzzles or the logic puzzle. So here, why we consider this task? So we wanted to work on a task that's more natural language and does not involve many symbols, and at the same time require multi-step reasoning. So far, I think multiplication and dynamic programming require mathematical reasoning and dealing with symbols, etc., etc. So we wanted to disentangle that effect of the English effect, language effect, and also the symbol effect, and try to work with a task that's more natural language, but at the same time, can be like multi-step reasoning is needed to solve the task. Okay. So for the Einstein puzzle, it's actually it's a very well known, I think, in the logic in solving constraint satisfaction problem, and it involves basically a list of houses, and with different attributes. For example, the name of the people, the sports that they play, for example, the car models, etc., etc. So there are list of attributes plus like a set of natural language clues in order to determine which attributes belong to which house. So we have this puzzle, which is a matrix of k times m, which is and then basically here we need to solve this puzzle using these clues. Yeah, so to construct basically the computation graph out of this, we consider a greedy algorithm that would actually iteratively eliminate possible solution by filling at least one cell, and then doing this iteratively until the full puzzle is filled with answers. So basically here, looking at clue 5 and 6, we can determine the name of people belonging to certain houses, the sports, the car, and we continue this iteratively until the whole puzzle is solved. So similar to previous task, and basically we try to generate this data set ourselves, try to make sure that the model doesn't rely on memorizing some answers from the pre-training data, and see the extent to which these language model can reason about these simple puzzle solving things. So yeah, we noticed that similar to multiplication, the performance actually drops. It performs quite well on some shallow problem, but it actually deteriorates to 0 when we increase the task. We also tried a few short examples, fine-tuning with the Scratchpad, and yeah, but like you see, like intermittent cases tend to work pretty well, but it goes to 0. So I don't want to spend too much time here, but you can find more details on all of these in our paper. Now, what I want to discuss is that I actually would like to move and talk about the failure and the success cases of transformers. Why do they fail and why do they succeed? And we noticed that in some cases, transformers predict partially correct answers, even when the overall response is incorrect. For example, here, although it might predict like this multiplication wrongly, but it still consistently predicts the first digit, the last digit, or the first 2 digits, the last 2 digits correctly. So we wanted to understand why this is happening. And so we sort of were able to, using the relative information gain to understand this correlation. So we measure the amount of information gained about an input element y, j, by observing a subset of input random variable. And we contrast this empirically to see whether there is like a correlation between the two observations. So here's what we notice. As I mentioned, that the model is able to guess the partial answer. For example, here, multiplying 49 by 37, you just do 9 by 7, you will see 3, and then that would be like the first digit. And you don't have to go through the full multi-step reasoning in order to solve that. So basically, we found a high correlation between the first digit using this information gain, the first digit of the output, or the first 2 digits, and the first digit of each input number in the input. The same here. In order to determine the last digit of the output, you just look at 4 and 3, and then that will give you the answer. So basically, looking at 2 branches in the entire graph. So this is great, right? We humans do that. It seems that these language models are learning shortcuts, which is totally fine. And humans, we use shortcuts most of the time. But the problem here is that we humans know when to use shortcuts and when not to use shortcuts. And it seems that these language models fall back on shortcuts most of the cases. And this can be super brittle, as we have seen. Like the minute they don't know how to apply the shortcuts, it actually fails. So this is something, and we speculate that these language models are picking up some of these shortcuts from the task distribution, so they're not able to distinguish between when to use it and when not to use these shortcuts. So yeah, this is to show you an example of how these language models excel at predicting partially the answer. For example, for the GPT-4 zero-shot, it's actually quite it's able to predict the last digit at a very high accuracy, the last 2 digits, and also trailing 0. If you multiply, let's say, 33 by 100, it's very easy to figure out that, okay, 00 should appear at the very beginning of the output. Yeah, so we have done more experiments about also information gain and predicting these surface patterns for dynamic programming and for all the other models using Scratchpad without Scratchpad, and we found the same observation basically. Now let's go back to the graph and try to understand how transformers solve a particular task. If we think about a graph, some model-generated answers will have a final correct output, and some others will have a very incorrect final response. So here we wanted to understand, the reasons behind the success or failures of language models. Is it because the model learned the underlying algorithm leading to the solution, or is it because the model was just exposed to similar training examples during the training phase? And this is why it's able to solve these. So the question we asked is the following. What's the correlation between a model generating a correct output and having seen relevant subgraphs during training? We noticed that for what we did here in order to investigate this. So we computed the average frequency of partial computation that appears in the training data needed to solve this task, and for both the correctly and the wrongly predicted examples. So the intuition here is that if a graph has been seen during training, the compositionality that's shown by the model performance is much less impressive because the solution can be easily extracted from the input-output sequences that are present in the training data. So what this means is the following, right? It means that the model might appear to do reasoning or multi-step reasoning, but in actually reality, it's just collapsing multi-step reasoning into simple pattern matching here. We found that transformer successes are heavily linked to having seen significant portion of the required computation graph during training. As you can see here, and we did these analyses for not multiplication and dynamic programming, but we also did it on the other task, the logic puzzle. This might question, certain concerns about AGI, and then these machines are really smart. Yes, they are still very, very useful, but they're still maybe relying on some other means in order to solve some compositional tasks. So you can see here that, the examples that tend to be solved and predicted correctly tend to have very high overlap of the subgraph training examples in the training data, as opposed to the ones that are wrongly predicted. So basically here, what I want to say is that some of the performance of transformers and their capability should be taken with a certain grain of salt, as they may not be relying on problem-solving skills, but rather other tools like pattern matching, which can be quite powerful and quite good, but it can lead to very bad failures in some easy examples. Here I also want to do a little stop about some previous works. Some previous work have talked a lot about shortcut learning and language models in different ways, but they, by and large, I think the prior work was based on weaker language models. And, some may have wondered already that with extreme scale, these problems can magically go away. And, these language models, especially GPT family models, now are capable of solving anything, given their impressive writing capabilities that we're seeing already, and everyone is using them. Basically in our work, what we try to do is to, we wanted to investigate whether we can empirically push the limits further and understand how do they work, and if they are actually succeeding in doing real understanding and reasoning. That's amazing, but we really need to understand the reasoning behind all of this. So next we studied the types of errors that these language models do, And we noticed that there are different types of errors. So first of all, these language models are able to do, to just fully correct means that the output and the ancestors are all right. And we noticed that these language models do a lot of local errors, meaning that the ancestors are correct, but the output is wrong. The second types of error is what we call propagation error, means that the model infer the right answer, but that is derived from the wrong, ancestors. And then we notice a lot of propagation errors, and I will just explain in a bit why. Also, one final error we noticed is the restoration error, and it was the most surprising to us. It means that the model is able to still predict the right answer, but without, but relying on like a wrong computational graph. The results here is the following. So we notice that the ratio of the propagation errors is higher than the ratio of local errors. And this indicates that the model is able to correctly perform a single-step reasoning, potentially due to memorizing, these single steps during pre-training, but fail to actually plan and compose several of these steps for an overall correct reasoning. So basically here at a very local level, these models excel, but they can't see the bigger picture, and at a global level they just fail, and they just keep propagating errors further and further. Okay, so yeah, besides these empirical experiments, we also theoretically show that these models can perform significantly worse in compositional tasks as the problem size increases. And this is from two perspectives. When we increase the depth of the graph and when we increase the width of the graph, these models, we notice that their likelihood to succeed is pretty low. Here, what I want to say is that it's very unlikely that using the same model architecture and the same objective function, we can achieve full mastery of these tasks. We noticed that we had two conclusions here. Transformers struggle with problems with increasing large parallelism, which is the width. So if you think of algorithms that are designed to solve compositional tasks, they typically involve multiple independent applications of a function. In our case, we think of transformer actually as a good estimators of these functions, right? So in this context, we examine the probability of such transformer reaching the correct answer as the problem size increases. And we notice that errors in early stages of this computational process can lead to substantial compounding errors in subsequent steps. And this can prevent models from finding the correct solution. Similarly, we found that transformers struggles with problems that require increasingly large iterative applications of the function. Here, we're talking about the depth of the model. So basically, if the model, does one mistake at one point, it's really hard for it to recover, and basically it will fail. So here, what I mean by inevitably leads to error, I mean that an increasing number of reasoning steps with exponentially increasing probability would lead to error with exponentially increasing probability. So basically, if the probability of making an error in a single reasoning step is epsilon, so the probability of success is actually 1 minus epsilon to the power of n. So it seems that in a nutshell here, what's going on, both types of errors accumulation suffer from the same phenomena. It seems that as long as we are using these language models, which are very good estimators of these tasks, they might fail if we're just gonna follow the same procedure or training procedure as we are currently doing. yeah, so here I recommend seeing our paper for all formalizations, including the probability of random error recovery. And yeah, here I want to actually, towards the end, I really want to conclude with a few thoughts. So some of you may think that, multiplication or other tasks that we investigated here should be just, edge cases, and transformer should be able to perform quite well on like other compositional tasks using just RLHF and scale, etc., etc. But here I wonder, as I mentioned a few times here in the talk, how about full mastery, like of these language models? How do we know whether they're able to solve fully the task without really evaluating with scrutiny the out of domain cases? And something here very interesting to also provide an answer to: how can we explain why transformers can struggle with tasks that are seemingly easy for humans, but excel at more compositional tasks that might be challenging for humans, such as writing a creative poem or a letter, etc., etc. So yeah, I think with that, I would like to thank all of you, and I'm happy to take questions. Yeah.
Thank you. That's really great. I love this idea like that you touched on right at the end of this dichotomy between like I can write a book with ChatGPT right now, but I can't add numbers or something. Like it's this crazy dichotomy between the two. But if nobody else has a question right now, I was curious. I read another paper also from University of Washington, I think, and it was about like how well, like measuring basically how well uh oh, sorry, there's a message in the chat. Oh, I'll ask this question and then we might end the recording in case anybody else wants to ask a question without it being on YouTube. But anyway, the paper was about how well do large language models solve like structured prediction problems, and the one that they used was part of speech tagging. And so it's like something that you can easily measure whether or not the model does well. And one thing that they were worried about was that part of speech tagging shows up in the training data for all of these language models, and similarly like multiplication would too. And so to get around it, they did a couple of experiments where they like prompted the model to do part of speech tagging, but they permuted the labels. So like they just like instead of doing like noun, verb, whatever, they just made up names for it. And I wonder if their model like basically it ended up doing almost as well as the baseline model. And like this sort of leads to my question of like, do you think that this is enough to avoid this shortcutting idea within the training data? Like, for example, if you had, instead of doing multiplication, you had just picked arbitrary symbols for 0 through 9. And then there's no way, like, unless the model can map between these two things, which there are other papers that show that, like, language models can't do swap operations, then this problem of shortcutting from like pattern matching in the training data kind of goes away. Did you guys do any experiment with that? Or you have any thoughts on it?
Yeah, no, we haven't done any experiments. I'm not aware of that paper. Now, to try to answer your question here, you're asking whether we like, so first of all, I think that there are two kind of questions here. The first one is like whether these language models are, how do we know whether they're just, I think, copying from the training data, and whether they're just, reasoning for, truly reasoning and things like that. And I think that's hard to know. And I mean, we noticed that we were partially able to figure out the answer when in multiplication the model was still outputting the wrong computation graph, but in some cases it will just output the right solution. So it seems that the model has seen the answer during pre-training, and this is why it's predicting the right answer. Now, by the shortcuts, I think it's pretty hard, and I think I have a different opinion. Like shortcut learning is great. Like even for us humans, it actually make us quite fast in solving a lot of problems. So I don't think that we really need to make these models, disable this capability in models, but rather try to understand how we can improve the interpolation and extrapolation capabilities of these language models, right? How to solve the length interpolation of these language models. How can they just, generalize from like simple rules to like from the same rule, from simple equations to like harder equations and things like that. So yeah, I think that if you try to, because learning these shortcuts is also a particularity of the task distribution. Like inevitably the models and human, when looking at a lot of training examples, they will pick up some patterns. And I think the way we're training these language models, they will automatically learn this. And I don't think that we should really try to disable this capability, but rather, yeah, as I mentioned, enable them with smarter algorithm, maybe to generalize better or something like that. Yeah, because, yeah, I will just stop here.
Thank you.
Brendan has a question.
Yes, thanks, Nouha. I really enjoyed. Great talk. I have two questions. One is a little bit about the computation graph and how that's generated. So I like the idea of having a depth and a width used to kind of measure the task complexity. I'm just curious. So you have a ground truth, say, an algorithm for multiplication, and you take this algorithm and you're trying to kind of measure the complexity of a instance of like 2 by 2, 3, or 4 by 1 or so, and then you generate this graph from the ground truth algorithm. Is that right?
Yeah.
Okay. So if you had a new so this is kind of if it discovers, say, a new algorithm for multiplication, and you're looking at the Scratchpad or something like this, how I'm just curious, how would you make sure that subgraphs kind of match this? Because maybe there's a different way to do multiplication, right? And it doesn't exactly match the data flow in the ground truth task, but nonetheless, it kind of still does the same thing. Do you think that's a possibility? And how would you measure the subgraph metric you were talking about?
Yeah. So that's a great question. So in our case, we actually try to do a few shot, whenever we use the Scratchpad evaluation, we try to do few shot examples with our Scratchpad version, which is the command that human use. And, so we make the model follow that Scratchpad in order to generate a solution, and similar for fine tuning. So we don't, it's true that the model might consider a different Scratchpad in order to generate the answer, but we haven't actually, we haven't tried that. We haven't really experimented with that in the sense, ask the model with a 0 shot to generate the entire Scratchpad and go through it, because it would be really hard for us to parse it, because every time the model can generate a different Scratchpad that may follow the same algorithm, but with like just a few differences that make it so hard for us to make this a scalable evaluation, to scale it up. So basically what we do is that we all the time try to teach the model this Scratchpad and try to see whether the model is able to follow the rule. Because if the model is able to generate another Scratchpad by giving some existing rule, it should be able to follow it. But what we discover is that the model is able to follow perfectly the Scratchpad rules when the model when the problem is not that complex, but whenever we just make it a little bit more complex, it just fails and just relies on some patterns in order to answer partially the answer and things like that.
Okay, I see. Yeah, so this kind of represents maybe like there exists a graph of this width and depth that can solve the problem. Maybe they're different. And the other question I had was related to, I thought it was really intriguing, the point you made about how complexity affects the generalization of learning. And I guess that can kind of intuitively make sense to me. I was wondering if you have a task which maybe there's no algorithm that exists, do you have any thoughts about how you would like a known algorithm, but maybe if there's a way to kind of rigorously test this hypothesis in the setting where we don't really know the source code for how to generate this graph, but we have kind of examples, so input-output pairs, I guess because it seems like this technique that you developed it works for things that we already know how to do pretty well. But maybe longer reasoning chains or things like this, then we don't know if there's like a drastically lower bound for the width or depth of the graph. So I guess so here it's kind of using length as a proxy for complexity, maybe the length of the multiplication, but maybe there are short sequences that have drastically different complexity, and the length really isn't a good proxy for that. So I was just curious, maybe if you had any thoughts about like training the same model on different tasks of varying complexity, and then measuring testing that hypothesis in a more general kind of say. I like the Einstein puzzles. That seems like maybe a little bit more harder intuitively to me than multiplication. But how would you kind of get a sorry.
This is a great question, right? Can we use the same approach, especially computational graph, in order to measure other tasks that we don't know the exact solution for? And that applies, I think, for more open-ended, solutions. Or so basically, I think the short answer, it's very hard. And I think this approach of using computational graph can really work for cases for which a deterministic executable problem can provide a solution, right? And this is where computational graph can be applied directly. But in the case where it's really hard to frame the task as a computational graph, you don't know the partial solution at every point, you don't know how different edges would change the partial answer in the computational graph, that would be really hard to figure out that. And it would be really hard to understand what's going on. And I really wish that we can do that. And I think here what we try to do, not only focus on some math problem that can be nicely framed as a computational graph because they have one precise solution, but this is why we try to also use the puzzle task, because it's a little bit more natural task, but it's still like very structured in the sense that there are certain cues, it follows certain patterns, and that's allowed us to frame it that way. We struggled a lot because one thing is the following, especially with natural language. These language models have seen almost maybe the entire web, if not more additional data. And it's really hard to disentangle whether they are really doing true reasoning or just, doing rote memorization on what they have seen. So that limited our capability to just, we were not sure how to do it, like, especially for like open-ended task, how to frame it, how to analyze that. You need to have like access to the entire web data or to the entire pre-training data, which OpenAI trained on. We don't have access to that. So for us, this was like a nice first step to use, this computational graph as a tool to understand deterministic executable program that have a very precise solution. And from there, we can maybe get inspired on how to do it on other tasks, or at least understand partially why they fail at a very simple task that humans excel at. Yeah.
Thank you so much.